A very warm welcome to everyone. We are the team from MVS Arts and Science Degree College, Mahabubnagar district. Our project is titled as Global Land Cover Change Monitoring System. This project was developed by I, Shashi Preetam Reddy, Anusha, Srujana, and Benhinn under the guidance of Dr. B. SambasivaRao. In recent years, we have been facing serious environmental problems such as irregular rainfalls, heat waves, water scarcity, deforestation, and mainly rapid urbanization. The main challenge is that these land changes are happening silently, and there is no simple way to know where the changes are happening, how fast they are occurring, and which areas are most affected. The idea of this project started during our academic visit to the Indian National Center for Ocean Information Services under the Ministry of Earth Sciences. During our interaction with one of the pioneer scientists, Dr. N. Srinivas Rao sir, who has specialized in remote sensing, while while we are interacting with him about satellite data, grounded data, he introduced us to a platform called Google Earth Engine, a cloud-based platform that provided large amount of satellite data and Google-based Earth data. The main advantage of this platform is we need not to download the large data sets to our local computers. We can directly access the data through our internet using cloud technology, which makes the work easier and faster. By taking this as an advantage, at the beginning, we started with a basic sample code that could only display satellite image and had limited features, and it was not user friendly or automated. From the starting point, we improved the system step by step and developed it into a fully interactive application. We added country, state, and district selection year-wise comparison, automatically land cover classification, area change calculation, and clear result with and report. We first tested our system using our own district Mahabubnagar, and after getting successful and accurate results, we expand the system from district level to state level and state level to finally to all country levels analyzations so that it can be used anywhere during development. We face several challenges such as interface problem like freezing in a full screen mode, performance issues, and improve accuracy. But through continuous testings and debugging, we successfully built a stable and fully automated cloud-based system. Now the user can know at which area, at which place, at which district, what is happening.
Let's dive into the software environment and implementation part of our project. We use Google Earth Engine as our main platform. It is cloud-based processing system. This allowed us to process large satellite data sets efficiently. For programming, we used the JavaScript APIs inside Google Earth Engine for automation, filtration, classification, and area computation. Coming to satellite data, we used Landsat and Landsat, where Landsat captures images during daytime using sunlight. But both Landsat and Landsat carry OLI, operational land imagery, and TIRS, thermal infrared sensor. Landsat 9 is the updated version with OLI 2 and then TIRS 2. These both satellites provide 30-meter resolution multispectral imagery, which is suitable for district level monitoring. Now let's move into implementation features. First, land cover classification is successfully completed. Second, spectral indices calculation, which includes NDVI for vegetation analysis, NDWI for water body detection, and NDBI for built-up areas detection. Third, automated land cover detection is completed, which reduces manual effort. Everything is done automatically. Fourth, area calculation. Area is calculated in square kilometers. This provides quantitative result useful for policy decision making. Fifth, multi-year comparison completed, where multiple years are compared together to give the result. Fifth, change detection analysis, where we identify increase or decrease in vegetation, water bodies, and built-up areas. Sixth, in interactive user interface, we developed an interactive system where users can select the year and region automatically. Seventh, administrative automation. We integrated country to state, state to district selection. For boundary data, we used FAO, Food and Agriculture Organization database. Finally, the entire workflow runs in the cloud. No local infrastructure is required.
let me continue the topic methodology. In this methodology, here we are having 5 steps. The first step is selecting the region. We need to select country, state, district as well as year to compare. After clicking on the run analysis, we get the data of selected region. The second step is image processing. In this image processing, it does 3 main things. The first is cloud masking. It will remove all the cloudy parts from the satellite image. It will give the clear data of land. The second is image correction. In this image correction, it will adjust the brightness and it will give the image accurate and clean. The third is composite generation. In this composite generation, it will combine all the images into a single image. Third step is spectral analysis. In this spectral analysis, the satellite like Landsat 8 will capture the light in the form of colors. This will capture the infrared lights. Suppose different surface will reflect different lights. Like plant will reflect more infrared lights, whereas building will reflect more shortwave infrared lights, whereas water bodies will observe all these lights. By using this idea, we calculated the indices like NDVI for vegetation, NDWI for water bodies, NDBI for buildings. The fourth step is land cover classification. In this land cover classification, here we are using thresholding value. The thresholding value is between +1 to -1. If NDVI having greater than 0.5, it is considered as high vegetation. If it is between 0.2 to 0.5, it is having low vegetation. If NDW having high value, it is considered as water bodies. If NDBI having high values, it is considered as high buildings. So, in this way we can say that by using thresholding, we get the clear data of land. Fifth step is change detection. It helps us to measure the value of vegetation as well as urban areas decreased or increased.
Let's get into model approach and validation. In this project, we did not use any AI or machine learning models. Instead of training a model, we use Landsat 8 and Landsat 9 satellite images which produce 30 meters resolutional data. We applied a standard remote sensing formula like NDVI, NDWI, NDBA. These all are scientifically proven. By those index values, we set a proper threshold limit to automatically classify the land cover. To make sure our results correct, we performed visual validation using satellite imagery, cross-checked index behavior for correctness, conducted a year-wise comparison and change. We also verified that the calculated area or in square kilometers was accurate. So even without using AI, our system produces reliable and transparent results because it is based on proven scientific method rather than a black box model. Let's jump into final prediction. If this current trend continues, water bodies may further decline, risk of future water scarcity, possible land degradation and economical imbalance. Continuous monitoring is essential for land and water management.
Conclusion: our project is evolved from the simple satellite image visualization into fully automated cloud-based global land cover change monitoring system. In this way, we can say that our project is providing solid contribution for societal beneficial like urban planning, sustainable development and environmental protection, etc.